Let me describe some examples of fault-tolerant procedures and what are non-fault-tolerant procedures. Suppose I want to compute a knot function. Well, these will be poor ways of doing them, and these will be good or fault-tolerant ways of doing that. So again, let's imagine that we encode in the triple redundancy code. So we have a number A that comes in, and then we perform 3 NOT gates. And if we run through a single majority voting gate and then copy the output 3 times, this is no good because there's a single point of failure. And this violates the idea here that a single component failure causes at most 1 error in the output. So we found, as you saw in the example, that a good way of doing this fault tolerantly is to have 3 majority voting gates. Like so. And this then is a fault tolerant procedure. Okay. If we're having multiple bits do something, and now let's start to use some of our quantum computing circuit terminology, and we want to compute a controlled NOT gate, classically still, but using quantum circuit drawing, this is either 0, 0, 0 or 1, 1, 1 when it's encoded. So clearly, if we wanted to, we could just perform a controlled NOT gate by using the top bit, because they're all supposed to be the same. And so if there were no errors, this would be a perfectly fine controlled NOT gate between 2 blocks. But clearly, if this wire failed, it would have another single point failure. So it's not a fault-tolerant procedure. Instead, one of the canonical ideas behind fault tolerance is to separate gates off into different bits. And this construction is called transversal gates. Transversal gate constructions. It just means do your gates bitwise in parallel. And this then allows errors only to propagate between the bits that are interacting together. And we will use the same idea for our quantum circuit constructions that are fault tolerant.